Hi, this is Sarah Steele, Lab Manager of Cole Science Center, and today we're going to show you how to film we're going to film GCMS. We're going to show you how to do GCMS. So, what is this machine, Sarah?
Yeah, this is called a gas chromatograph mass spectrometer, or GCMS. So on the right half here, we have our GC, or gas chromatograph. On the left half is our mass spectrometer, or MS. So a quick rundown of what this machine does is we take a sample that can easily go into the gas phase, and we'll inject that onto this machine. The sample will travel through a column on the gas chromatograph, and all the constituents, or all the components of that mixture, so if you have multiple compounds in there, they'll all travel at a different rate across the column and get separated. They'll come off into our mass spectrometer, where our mass spectrometer will cause the compounds to break apart and ionize, and then it'll count the types of ion fragments that are forming.
And then it'll show up on this computer.
Exactly.
So what's in here?
Yeah, so when we go to inject a sample, I'm just going to lift this up so you can see. We have, this is a helium gas line right here. So there's always a constant flow of gas on the gas chromatograph. In chromatography, you always have something called a mobile phase and a stationary phase. The mobile phase, in this case, is helium gas. That basically sweeps our samples along through our stationary phase, which is a column.
Woo!
So this is about 30 meters long. So when we inject our sample, so we have this syringe we're going to use to inject a sample. It's a 10 microliter syringe, and we only inject anywhere from 1 to 3 microliters. So teeny tiny amount, like literally a drop.
Yes, and here's our station where we inject it.
Which is rather messy right now.
Oh, that's fine.
Yeah, so when you go to inject a sample, we load it into here, and then we come up here. So this green nut right here has, right inside of that, there's a thing called a septum. A septum looks like this. And this sits right inside that green nut. So when you put the needle through there, you'll feel resistance, and that's the resistance of the needle going through the septum. The septum exists to keep air and water out of the system, because we know air and water are our enemies in this. We don't want air, we don't want water in this system. So when you inject your sample, you go through the septum, you go all the way down, and this needle goes into what's called a liner. The liner looks like this. So picture this sitting like basically right here underneath that nut and before the top of the column.
Yes.
So when you inject your sample, it literally goes inside like this. And then you inject, when you inject your sample, it goes inside the liner like this. You inject the sample, this liner is heated to 250 Celsius, so your sample instantly vaporizes inside of this. And then that helium gas I was talking about comes in from the top and sweeps your vaporized sample down through the bottom of the liner and onto the column. So this is where the bottom of the liner is, right up here. And then your sample gets swept onto the column. And that helium gas is constantly flowing, so that provides movement, so that your sample travels through this. The different components of your mixture, so you have methylene chloride usually, which is your solvent we dissolve our sample in. In this lab we have benzoic acid. So in theory, all we have in our sample is benzoic acid and methylene chloride. Those will separate and travel at different rates based on their molecular weight, based on how they interact with the column. They'll go through. The methylene chloride will come out into the mass spectrometer first because it is very light. It only weighs 84 grams per mole, and it's pretty inert. It doesn't interact with the column at all. So that will come off into the mass spectrometer. And unfortunately, I can't open up the mass spec to show you what it looks like inside.
That's okay.
But when your sample goes into, say that methylene chloride comes out, when that gets into the mass spectrometer, there is a little filament that looks like this. Is that?
Yes.
Okay. So there's a thing called the ion source. So you can picture your methylene chloride as like this little cloud of gas of dichloromethane. It goes into a tiny little opening, and then this filament fires off electrons. This is a tungsten filament.
Pew, pew.
Exactly. I find it interesting. It's like an incandescent light bulb. A voltage is applied across these two electrodes, which then causes that tiny little filament, which is made of tungsten, to spew out electrons. Those electrons collide with the molecules in the gaseous form and make them break apart into pieces. And the way a molecule falls apart tells you something about how it's put together. So then after it's ionized, it goes through some different lenses that select for the different ion fragments. Mm-hmm. And then the mass spectrometer will then accelerate those ion fragments down what are called quadrupoles. All of the ion fragments that we can detect have to have a positive charge. So when the fragments fall apart, they're often missing an electron, which can cause a positive charge. And then they get funneled down to a detector that counts how many times it sees those ion fragments. So this is a used detector. And if you can see in the very center, that inky black void, that is where all the magic happens with the detection. So when we're looking at our data on the computer, we'll see data for the GC. It shows up in a thing called a total ion chromatogram. And that shows you the sum of all the ion fragments at each point in time, with time being on the x axis and abundance being on the y. And our mass spectrum data shows us all the ion fragments present at any one point in time.
Okay.
Okay, so that's that. All right.
Hi. So this is part 2 of the GCMS video. This is going to be showing you how to actually make the sample. Well, not make the sample, but put the sample in the GCMS machine, as you see over here. So here we have our station, and I'll zoom in here. We have a waste container, we have an acetone wash container, and we have the sample right here that we want to use. That's benzoic acid dissolved in dichloromethane, and you're good to go.
All right. So we're going to be injecting 3 microliters into the GCMS. So the first thing we're going to do is wash this syringe 10 times with acetone. And what that does is it ensures that the syringe is nice and clean inside. So the way we wash it is we start out by pulling up about 2 microliters into the waste, then about 4 into the waste, then 6, then 8, then 10 microliters. Once we've done that, we'll do 5 full-length rinses just to make sure that we've washed out any potential contaminants and really thoroughly clean this thing out. So I'm going to start now. So I'm going to start out by pulling up about 2 microliters. And you're going to see, you can see that this is literally a drop of liquid. Can you see that?
Yeah.
Yeah. So it's not a lot. All right. Now I'm going to pull up 4 microliters into the waste. Then about 6. Then about 8. Then about 10. So that's been 5 rinses. Now I'm going to do 5 full-length rinses. So 1, 2, and when I'm rinsing, I'm being careful not to touch the needle tip to anything that might bend it, or touch it to any surfaces that might contaminate it. Was that 4 or 5? I lost count.
That was 4.
So this is 5.
Yep.
Great. All right. So now I'm going to cap the acetone so I don't accidentally knock it over. The next thing I'm going to do is do 3 washes with our sample. Because I'm only injecting about 3 microliters, I'm only going to rinse about half full. So I'm going to pull up somewhere between 3 and 5 microliters. And again, I'm just going to be careful not to touch the needle tip to the waste container, stab myself with it, stab anything with it, you know, be careful. So that's 3 rinses. All right, so now I'm going to stand up. Now that my quads have gotten a workout. All right, so then I'm gonna hold this.
Okay, we're gonna.
Okay, so I'm gonna hold our vial in these fingers so that I can then put the needle in here so that the needle is below the liquid level but not touching anything, and then I can stabilize it with my fingers so that I can just like, it's hard to see that, but so I can hold it so it's not hitting the bottom.
Yeah.
Because the next step is you want to get air bubbles out. So you plunge this plunger up and down really fast like this. Do that for a little bit, then you stop and slowly pull up. I don't know if you can see that, but there's an air bubble in there. We don't want air bubbles. So that's why we do this plunging thing. Stop. Carefully pull up. Ah, there's an air bubble. Try it again. When the needle tip gets bent, it makes it more likely to trap air bubbles. And I think that's actually what's going on, is that this needle has been used a lot, so it's bent a little bit. So I just push some stuff out that helps push an air bubble out. There we go. Nope, there's an air bubble. Okay, now we're good. I've got 3 microliters, so I'm going to hold this so that the plunger doesn't fall down under gravity. And then I'm going to come on over here, and we're going to do this manual injection. So we're going to go through this septum nut right here. Ready? I'm going to push this down, push the plunger in, pull this out, and hit start on the GCMS. And you want to do that all in one smooth motion. And when you do that, then the analysis starts. And then we have this window here called override solvent delay. What this does is when we inject our sample, the sample instantly vaporizes. Most of our sample is made up of methylene chloride, and that travels through the column fastest. That's called our solvent front. When that solvent front comes out, there's so much signal in there that it basically blasts out the detector if you have the detector turned on. So unless we specifically are looking for something that might come out within the first 3 minutes, in our solvent front, we keep the detector off. It just saves wear and tear on the detector. So in general, unless you're told that we're going to need to override the solvent delay, just ignore this box and let it do its thing. The detector will turn on after 3 minutes. And you can see here where we're at with the analysis. We're about a minute into it right now, so we still have about 2 more minutes to go. All right, so then after you inject your sample, we have to do 10 more rinses with acetone. So we always wash our syringe before and after we run. So this just gets it nice and clean for the next person. But also when you come to run a sample, you don't want to trust that whoever did it last did a perfect job, right? You always want to wash before and after. So I'm just gonna, once again, pull up about 2 microliters. Pull up about 4, pull up about 6, about 8 microliters, and now 10. And then I'm going to do 5 more rinses full length. So 1, 2, 3, 4, 5. All right, and then when you're done, just make sure to cap all the vials again so that we don't have open vials of solvent hanging out here. There you go.
Now that Sarah and I have shown you how to make a GCMS sample, it's time to interpret the results. Here's the gas chromatography graph for all 28 minutes that the sample ran. At 12 minutes, you can see there is a massive peak. This means that the mass spectrometer read that most of the fragments of our sample split apart and were read at this point. I printed out the mass spectrometer peak at this point, and I'll point out the main peaks that I think could be interpreted as benzoic acid. Here's where I pointed out the 3 largest peaks on the mass spectrometer graph. Peak A, which is 77.2 grams, is what I believe to be the fragment C6H5, which is the aryl ring from benzoic acid. Normally, benzene has 6 hydrogens, but the 6 hydrogen in benzoic acid's aryl ring is replaced by a carboxylic group. To do the math, 6 carbons is 72.06 grams, and 5 hydrogens is 5.05 grams, totaling to 77.11 grams, which is quite close to the 77.2 gram peak. Peak B, which is 105.2 grams, could be the ion fragment C6H5CO-, which is the aryl ring and a carbon-oxygen double bond, which totals to 105.12 grams. This fragment lacks the alcohol group that would complete the molecule, but that's where peak C comes in. Peak C totals at 123.2 grams and is the full molecule of benzoic acid being read in the spectrometer. If you add an OH group, which is 17.01 grams to peak B, you get 123.13 grams, which is incredibly close to the weight of peak C. These peaks in total indicate that the benzoic acid I synthesized is decently close to pure benzoic acid. Although not perfect, the main fragments I pointed out contain parts of benzoic acid that matched up with the molecular weight of those fragments. These smaller peaks seen on the graph indicate impurities in both my product and the GCMS machine, which is perfectly okay. Synthesizing a pure compound on the first try is incredibly unrealistic, so I would say these results are great for a liquid-liquid extraction. Thanks for watching, and I'll see you in the next video.